Oh, it's
now it's on.
Thank you. So again, I would like to thank the organizers for inviting me. And this has been a wonderful conference. It's my first time at IGST, and I've had a lot of fun. So I'll be telling you mostly about some work in preparation with my collaborators, Prokopi, Volodya, and Harish. But I'll also say that there's been some earlier work that has addressed some of these things. In particular, last year, there was this paper of Kazakov, Harish, and Pedro. You might have heard about it last year in IGST. So there's some updates to this, and you might not be aware, but I also worked on this before. So what am I going to tell you about? So before I tell you about anything, usually when people talk about ADS-CFT, they like to say that there's a natural hierarchy for operators. So for n equals to 4, at least in the half BPS sector where I know what I'm talking about, people will say that, well, depending on how the dimension of the operator scales, you get different things in the bulk. So if delta is of order 1, you should expect that it's some kind of graviton or some KK mode. Usually people say operators with dimension of order n are giant gravitons, and operators with dimension of order n squared are dual to geometries. Great. But if you work on this seriously, you realize that there's always a lot of caveats to these statements. So, for example, the single trace, there's mixing between single traces, so the KK modes are really dual to some kind of complicated combination of single trace operators, and well, actually multi-trace operators. The giant gravitons, really, the classical solutions in the bulk are dual to superpositions of these operators, not to particular operators. And really, my point is, more importantly, that for the geometries, not every operator with dimension of order n squared is dual to a geometry. It really has to be generic enough. Okay, so what do these things mean? So some questions you might have when you're working on this is, well, what kind of operators can I even play with this game? So could I take something like trace c to the k to the n squared, or trace c to the n squared, or combinations of these things? And if I do this and I somehow manage to compute correlation functions, how do I see the shape of the geometry that's dual to this operator? And I think what's really the hardest question is, how do you do the opposite? If there's a geometry that I want to prepare, how do I prepare the state in the CFT? And really, it would be nice to be able to do this efficiently. If you're more ambitious, you might want to do this in less supersymmetric setups, but okay. And basically today I'll try to answer this four points and give you some hints about this last one. Okay, so why is large n hard? Well, here we usually talk about when people say n equals to 4, they drop the planar n equals to 4. So even in the free limit, n equals to 4 Young-Mills is not really a free theory. For example, you can look at this correlation function and you find that there's mixing between different multi-trace structures. So it's really a free theory with constraints. So you should think of it as some kind of topological theory of interacting strings. Of course, in a planar limit, this is not an issue. But as soon as delta gets really large, these effects can't be neglected. And eventually, they actually overpower everything. So how do you solve this problem? Well, the honest approach is to diagonalize two-point functions, find operators that have properly orthogonal, do it in the free theory, and then if you want, you can do perturbation theory. So for half BPS operators, this was beautifully done by this paper by Corley, Jamik, and Rangulam. There's a basis of orthogonal operators for UN. So it's a beautiful solution. But already, if you add one more matrix and you start to ask generic enough questions, these techniques get really, really intractable. So if you want to see what these things look like, there's a recent review by Demilokov and collaborators. So I'm not going to be honest. Instead, so the reason this problem is hard is because you're asking for exact orthogonality at every n, and that's very hard to do. So instead, I'm going to ask for something that's closer to approximate orthogonality. So I want states that don't have sort of delta function. Well, yeah, so the two-point function of two operators is approximately a delta, and then there's a kind of exponential tail to when it's not. Yeah, I think that's the typo. And some of my collaborators, and for instance, Bernstein, we have been trying to develop tools to address these problems in BPS sectors, in particular, half BPS, core BPS, etc. Yep. So what are some kind of operators that you should keep in mind that I'll be talking about? Well, you could, for instance, try to come up with these combinations, something like this. Like you could try putting a potential for C. So this is what we call exponential operators. Now, I'm not the first to think about these things. At least in this context, the first time this appeared was in a paper of Sam Vasquez in 20 years ago. There's, of course, the orthogonal basis. And the thing that I'm more excited about are these coherent states. Okay. So none of these, except for the characters, none of these have definite dimensions. But I hope that you appreciate that this is not really a bug. This is something that I want. Okay. So half BPS operators. So, well, in general, half BPS operators, when people talk about them, are just spanned by multi-traces of a single complex matrix. So essentially, this was known for a long time. This means that the Hilbert space of half BPS operators is isomorphic to n-free fermions. And it turns out that so n-free fermions in a harmonic oscillator. So you can think of a wave function of one of these free fermions as being some kind of distribution in the large N limit. And this is where a lot of people got a lot of mileage here. They used this implicit duality to these free fermions, and then they would compute. But actually, it's not very easy to reduce honest correlation functions to the free fermion description. But this description is quite nice because it's quite explicitly matching the dual supergravity solutions. So clearly, if you give me an operator that's excited enough, it will lead to a density of eigenvalues, and that gives me a geometry. But how to do the opposite is a bit more tricky. And the simplest things that you can think about are 3-point functions of these half BPS operators. And just by symmetry, so these are not, in general, primary. They're going to be sums of structure constants with some kinematic functions. For now, I will set this essentially to 1. And it's known that these structure constants are independent of the coupling. So sometimes when I talk to people, then they go, well, this is not really interesting. There's no coupling dependence, so they're trivial. But there's really 2 parameters. There's n, and that's a different kind of coupling. Okay. So a lot has been done before. I'm not the first one to look at this. So for example, for structure constants of 3 light operators, essentially, I would say about everything is known in the large N limit. For correlation functions of giant gravitons and light operators, I would say we know most things. Other things you could repeat are more complicated. And really, we know very few things about heavy light, especially on the gravity side. So today I'm going to tell you about these heavy light operators, more importantly, these heavy giant correlation functions, and maybe some things about heavy. Okay. So what's the trick? The problem with this kinds of calculations is that if you're doing things honestly, you're doing a lot of weak contractions of free fields. And operators are normal ordered, so you either have to be very smart at combinatorics or you have to do things by hand, and it's very tedious. So it's always useful to try to come up with a different perspective of a combinatorial problem that might help you solve it. So here the trick is, well, we want to map this to some kind of matrix model because we know that at least the spectrum is related to free fermions, so there should be some matrix model description. So first, I'm going to write down the most naive thing that I could write down. So I'm going to replace all the scalar fields by matrices, drop all the space-time dependence, but keep the R symmetry dependence. And then you can ask, well, what's this integral? What's the value of this correlation function in this Gaussian ensemble? And at first, this was a complaint that I had about this. This couldn't possibly give you the right answer because these are not operators. They're not normal ordered. But actually, because of this, these polarizations are null, you can easily see that if you do weak contractions between this operator, they'll vanish. And similarly for the other two. So the only things that this computes are basically weak contractions between O1, O2, O1, O3, etc. So this is exactly the same combinatorics that you would get from, say, doing this in free Yang mills. Okay? And then you can use the Birkenfeld symmetry to fix your polarizations to be your favorite. So I can pick the first operator to be made out of C's, second one to be made out of C bars. And for the third one, I'm basically left with this freedom. And then you just integrate all the things you don't want. And very clearly, this is going to give me a matrix model for C and C bar. But OK, we still have to work because these things don't commute. So you can't reduce it to eigenvalues. But OK, you go and do a lot of work. You go open some books about complex matrix models. And you see that the right thing to do was this short decomposition, and that you should integrate over these upper triangular parts of the matrix. And luckily, for all the things that we care about, these things are Gaussian. So we can actually just do the integrals. And we get something like this. So now this is a purely eigenvalue expression of some different function, which we call the Q transform of the operator. So it's given by this integral, which you really should think of as some kind of normal ordering. So if f was some kind of trace of x to the k, this would be some matrix analog of a Hermite polynomial. Okay. And the point is, we can do this by hand. We can actually compute these things explicitly. And OK, so the strategy is, at least for heavy, heavy, light, heavy, heavy, giant, you determine the distribution of C's from the integral, and then you evaluate this last operator in that distribution. So first I have to tell you how to get that distribution. This is a well-known problem. Usually these things are referred to as Genevri ensembles. So here I'm going to be formal, and I'm just going to say that the potential is the log of the operator, but this doesn't change the argument. So the saddle point equations for this come from an effective action and the large N limit. And the only important thing is that this V and this V bar are holomorphic and anti-holomorphic. Because then the saddle point equations will tell me that this rho is constant. So it's going to be constant in some domain, possibly disconnected. And so the problem is, how do you reconstruct this domain? So this is a well-known problem. This is Laplacian growth. And it turns out that you only need holomorphic data to reconstruct. So for example, you look at a character. This is what the matrix model would look like. The saddle point equations have this solution, and you find that the distribution is some kind of concentric ring distribution. So this was well known. If you take something like a cubic potential, you can play around with the parameters, and you can make all kinds of shapes. Again, this is well studied in matrix models, so I'm not going to dwell on this. But the ones that I do think I need to dwell a little bit on are these coherent states. Because, well, in general, if you look at this expression, it's some messy determinant. So you would really think that you would have a very hard time finding the saddle point solutions to this. But it turns out that these things are, they're coherent states, and I keep calling them coherent states. So because they satisfy this coherent state condition, if I apply the C-bar operator on the state created by a coherent state, it just returns the same function with a scalar. Okay. So if I assume that the saddle point condition still applies, and then I use the coherent state condition, so I compute the expectation values some holomorphic quantity. A large N, I expect that to be an integral over the density. But I know that because it's a coherent state, it's actually given by a sum of these coherent state parameters. So what you do is, well, you push this integral to the boundary, and what you find is that, okay, there's poles. There's poles at the positions lambda I, and essentially, I mean, the math words are that the Schwartz map of this domain has some poles and some analytic part, and yeah, so the point is you can actually reconstruct this shape. So for example, take the simplest distribution of these lambdas that you could think of. Say I put n over 2 of them at some point alpha, n over 2 of them at some point minus alpha. So the moments are always going to be given by this. And in that case, so you plug this into this formalism that I was talking about, and you find that the shape of this algebraic curve of the boundary of the droplet is given by this. And so in math, this is called the Neumann oval. But in physics, this geometry was actually already considered by a paper of Skeders and Taylor. They call these Riplon geometries. So this is the case for k equals to 2 of this Riplon geometry. So what does this thing look like? If you take alpha to be close to the origin, it looks essentially, this is not quite a disk, it's a little bit shifted. And then you keep messing with it until they kiss, they disconnect. So essentially, I can make any kind of disconnected domain with these coherent states. And of course, I mean, I can put different numbers of eigenvalues at the nodes. It doesn't change anything. And in fact, I can put any kind of distribution. As long as I know the analytic structure of the distribution, I'm able to find the conformal map to whatever the shape is. So for example, this distribution is a semicircle for the lambda eigenvalues. And it turns out that the shape of this domain is an ellipse. So for this distribution, it actually just reproduces the quadratic potential. If you take a uniform, sort of like a line of charge, you get some kind of oval shape. I don't think it has a name. Okay. So basically, in general, if I superimpose these coherent states and I take the large N limit, I'm able to get more and more of these nodes. So I get more general quadrature rules. And then depending how I play with these things, I can get higher order poles and so on. So if you look at some theorems about these quadrature domains, you find that these things are dense. So actually, I can, in principle, reconstruct any shape with these coherent states. So that solves the problem that I was telling you about. But okay, in practice, you might find multiple domains with the same moments. So you have to pick the one with maximal action. We haven't encountered one of these examples yet, though. But they do exist. Okay. So let's do all the heavy light operators now. So I know how to get any kind of density now. Now I just need to find what the right things to put in the matrix model are. So you look at these kinds of expressions and you open the book by Ikami and Bressan on background field methods, and they tell you all these formulas on how to compute these kinds of things. So, okay, here I give you the first 5. In the large N limit, okay, the first one is given by trace x. X is QC plus QC bar. So it's a Hermite polynomial. The second one is a Hermite polynomial. Third one is a Hermite polynomial. Fourth one is not a Hermite polynomial, but it's a sum of Hermite polynomials. But okay, everything is a sum of Hermite polynomials. But these coefficients, I mean, if you look closely, these are basically binomial coefficients. They're just entries in Pascal's triangle. So I think there's a lot of structure here that is not really obvious. Okay, so you go and you expand in this parameter Q to extract the different charge sectors. You go and work out the normalizations, and you get these kinds of expressions. And then you open Skeders and Taylors, and you find that this is exactly what they find. Up to some normalization. So to me, this seems to say that there's a lot of hidden structure in these correlators. Somehow, maybe there's a This suggests there might be a simple way of doing this calculation, Scudder's and Taylor, but I'm not sure. Okay, so now let's replace a trace by a determinant. Again, you just basically plug this into the formalism, you crank the thing, and you get some expression in terms of eigenvalues. Okay, and then you integrate, you get at the end, say, a structure constant of some representation R, and some subdeterminant of rank delta. You get this kind of integral. Here H is related to the Young diagram. So this matrix is not very clear what this is until you work out a couple of examples. So if you have a Young diagram like this with 3 blocks, it turns out that this matrix will have 3 blocks. The size of the blocks are related to so these heights, and these L's are essentially the distance to these corners. So because it's block diagonal, it just reduces to each of these blocks. So it factorizes. And for each block, you get some tridiagonal matrix, so the determinant satisfies the recursion relation. And if you've worked with matrix models a lot, you recognize that these are orthogonal polynomials. So in this case, these are associated Hermite. Okay, so again, you open the textbook and you compute. So that's the value of the structure constant, and this is exact. Okay, but I said I wouldn't do combinatorics. So how do I get this a different way? And the point is that the expectation value of this determinant in the C ensemble is related to the exponential of the resolvent, the integral of the resolvent of the density. And I call it P because you should really think of it as a momentum. And this expression is just the WKB approximation of the orthogonal polynomials I was talking about before. Okay. So you can plot these things. They don't look, so this gray line is the exact integrand for some parameters. You plug in the asymptotics, they don't look too good. But of course, it's because you're only looking at the asymptotics. You're not looking at the fine grained details. Okay. So as we heard yesterday, usually when you get oscillatory integrals, you have to deform your contour and go through a complex saddle point. So that's what happens here. You deform your contour, you find a saddle point for this integral, and it's given by this in the end, where this B and this A are the radii of the ring distribution that's created by the big operators. Okay. And this you can rewrite like this, but okay. And this is actually exactly the asymptotics of the previous expression. Okay. So unlike single trace operators, these things grow exponentially. So I expect that if we were to compute this in gravity, the only thing that you would get to leading order is the asymptotics. And because it grows as e to the n, it looks like a D3 brane, but it can't be a full D3 brane, so it has to be some kind of instanton. Okay, I'm not gonna bother too much with this interpretation, but the point is that essentially there's 2 contributions to this OPE. One of them comes from an integral over the density, which I call the sort of a bulk part. And then there's an integral that only depends on the data of the dimension of the operator that you're measuring. So this is some kind of boundary condition, some kind of boundary term. And there's always this common alpha squared plus epsilon over 2. You can always check that this is inside the distribution. So this to me says that there's some kind of hole in the distribution. Okay. So now I'm just gonna, actually I went too fast, but I'm gonna flash some other things that we can do. So I think last year, Harish gave this really nice talk, short talk, where he was working on the numerics for heavy correlators. And I think last year he showed you a plot where he had these dots making this shape. Now we actually have the analytic solution. We have the solid line, and that's the actual eigenvalue distribution for this potential, at least when you take the operators to be determinant C to the n. Okay. We can also do this with cubic potentials. So Prokopy very heroically worked this out. So this is the density. And well, here you have two parameters, so you can play around and you can tune the thing to a critical point. So you find that at least this correlation function seems to have critical behavior that's similar to the three-state pulse model in 2D gravity. Okay. And now, okay, the thing I would really like, I hope there was a lattice person here, but I don't think there's any lattice people. So now, Coherent BPS operators. It turns out that there's a natural generalization to these coherent states that I was talking about to the Coherent BPS case. Now, in general, I don't know of any construction of Coherent BPS operators in n equals 4. As far as I know, this is a very hard combinatorial problem. So this, in some sense, is a generating function, but we don't know what it generates. So if you take this coherent state and you set these coherent state parameters to commute, you can show that this is annihilated by the dilatation operator up to 2 loops. We can't check 3 loops because we don't have the non-planar dilatation operator at 3 loops, essentially. And in general, these things will lead to unsolvable matrix models. I tried very hard. Me and my collaborator tried, and we couldn't make a dent. But they're still coherent states, so they still satisfy this nice condition where as long as you take expectation values of holomorphic observables, they're only replaced by by proper scalars and not operators. So I somehow expect that these things are related to, at least approximately in the larger limit, they should be related to commuting matrix models, but I don't know how to make this precise. But if you could do this, and I think in principle you could ask this question of how can you reconstruct the dual geometry to one of these operators? And it would be very similar to what the half BPS case, how the half BPS case worked. I don't know how to do this, and actually the duals for these operators are very complicated. And another comment is that these kinds of integrals seem to be related to what you would do if you did a quenched Taguchi-Kawai reduction, the principal Carroll model. Unfortunately, the quenched Taguchi-Kawai reduction doesn't seem to work even for gauge theories. I think it's the people that seriously work on this, I think they don't believe that this, well, never mind that, but they say it doesn't work. But there's a working model of this Taguchi-Kawai reduction, which is a twisted Taguchi-Kawai reduction. And there might be some relation between that and the beta to form n equals to 4, but we don't know. Okay, so conclusion, BPS coherent states are very nice. They allow you to control essentially the whole parameter space of the Hilbert space very explicitly. This should be a similar story for core BPS operators, but I don't know how to, essentially, I don't know how to deal with these matrix models. I showed you some examples of the things that I could do. So these are, I cherry-picked one correlator that I could show you explicitly, but in practice, you could do whatever. Like, for example, if you pick some potential, you should expect that the recipe tells you that the expectation value of a determinant is going to be related to the orthogonal polynomials of that potential. So we can compute these things. I think at least in the Salomon approximation, I think now I understand that we can really do this explicitly. But we don't really have a very concrete gravitational interpretation for these things. And I think it would be very nice to work this out. You should also take this as evidence that large N superangles makes sense, not only in the planar limit, and it might have a controllable semi-classical expansion. Okay, I talked a lot about free fields, but I could have just replaced free field with chiral algebra and everything works. So I think This is not special to these half BPS operators. This is something different. Okay, so thank you.
Are there any questions?
So just a bit technical question. So you show that like a normal ordered version of the trace of some power, like a trace of some like a field to some power
Yes.
is some linear combination of Hermite polynomial. I thought like it's more related to Chebyshev, but maybe we are talking about something different.
That's what happens. I'm not. So to be completely honest with my Mathematica skills, I was only able to get to 6, and there's this pattern. Harish claims he can get up to very high numbers, but we haven't checked. But for sure, so the Hermite polynomials come from this normal ordering.
Mm-hmm.
So that one definition of the Hermite polynomial is you take the moment of x plus I y to the k. It's that kind of thing.
I see. So you don't see any relation with the Chebyshev?
Not here, but I know that, I mean, when we were computing these other things, we got all kinds of Jacobi polynomials. So I right now I don't see the relation, but maybe.
Well, if there are no more questions, let's thank Adolfo again.
I will have some events happening.